basically, you know, whenever you have two systems, and one of them can have two states and the other can have 10 to the 20 states. If you single out two states in this system, they are going to be correspondent two states in the other system. And they will be pure. And now by rotating the basis in system number one, you can look for the situation where things both here and there are orthogonal. And it's a fantastic theorem. I mean, it's really exceedingly useful and should be taught. I think Quantum 101, probably even. And it's algebra. Schmidt, 1905, before quantum mechanics, so it must be true. Question?
Out of curiosity, are there any experiments where you have some system that's like effectively closed, and you can focus in on some small piece of it such that the rest of it serves as an environment and classicalizes it, but the entire system can't classicalize because it's effectively a closed system? Is this possible to observe such a setup, or is it way too difficult?
So I know of experiments, there's a beautiful experiment, I kind of skipped them on transparency, where you have actual environments, right? But I mean, you don't control it, right? I mean, I think the first experiment we confirmed decoherence were done by Serge Jaroche in Paris, and then there were beautiful experiments, and he had microwave cavities through which he was running Rydberg atoms, and Rydberg atoms were entering in superposition, and they were putting the photon modes in a cavity into a superposition of two coherent states, which were, you know, and this is a piece of art, and then Anton Zeilinger, who has fullerenes, and looks at the superposition, and he can, for example, heat them, right? So the fullerenes emit while they travel, and the decoherence is because of the memory of which parts they went. That's left in the radiation they had emitted. Right? And so there's a sequence of these. But I think it's very difficult to have a system, the environment, and that thing enclosed. Right? And I think, you know, things which are coming up are pretty amazing. And yeah, in fact, you know, we are trying to do something like that with Ulm, with MEV centers. So these are vacancies in a diamond which act as quantum systems, right? And you can get them to talk to each other. And we are trying to have a situation where we have, you know, one central system and a couple of guys on the outside that are acting as the environment. The problem is that the rest of the thing is also acting as the environment, right? So isolation is a tall order.
So when you say that the coherence is covered by the system environment interaction, well, in order to define what the right factorization of your Hilbert space is and what you call system and what you call environment, you usually do it in such a way that the system Hamiltonian and the environment Hamiltonian are dominant with respect to their interactions. So they have faster time scales.
Yeah. But, I mean, not always, right? I mean, if you have a harmonic oscillator, you have a harmonic, if you have a pendulum, right? I mean, it's got fairly dense energy levels, right? And in this case, you're going to have a situation where, and it's an underdamped pendulum, and I think it's going to be reasonably well represented by the sorts of models that you know, a number of people, including quantum mechanics, have solved with increasing degrees of rigor and accuracy. Right? So you have situations where you know, the system and the Hamiltonian and the interaction with the environment exert comparable or negotiate the sort of least preferred states, the pointer state, right? And you know, it's very clear that in that situation, you can solve it, right? You know, you put something in a superposition being here and there, and it's going to decohere very quickly. But if you had just, you know, a coherent state which is hanging around here, it's going to evolve. I mean, the other, you know, exceedingly nice example, which I like because it ties in with statistical physics, is quantum chaotic systems. So quantum chaotic system is really classical system which is classically chaotic quantized. Right? And they inherit some of the features of funny evolution from the chaos that would classically spread their states through the phase space, but because, you know, in absence of the environment, purity is preserved, they end up getting contorted into all sorts of weird superpositions. But in the presence of and these weird superpositions end up evolving in a way which has different expectation values than what you would infer from classical. Right? But if you introduce decoherence, the expectations values coincide. So it's nice.
Is the assumption that you can write states of the system as a direct product, is that a precursor to being able to define what you mean by an apparatus, or separation between your system and environment?
Yeah, so there is a question there, right? So and it's I think a question which worried me forever, and I do not have a good answer. So let me give you the answers that I do have, right? So you know, all of that is based on the idea that system is the environment, right? On the other hand, if you do not have a division between systems in the universe, you do not have a measurement problem. The whole thing evolves nicely according to Schrödinger equation, deterministic, right? So the measurement problem arises when we have a separation of the universe into systems. And then, you know, you see here's an apparatus that it somehow got correlated with a system, but it also ends up looking like it's in a definite state. Right? So in other words, in order to define the problem, I need systems. So I do not feel guilty assuming that system exists and trying to solve the problem. But I think the question of, you know, how do you define systems in a fundamental way is a good one, and I've been thinking about it on and off for quite a while, and I mean, it's very clear this is not going to give you a law, right? I mean, you know that if you turn the knob on electromagnetic interactions, or on, I don't know, constants in Yang-Mills theory, what you call systems is going to change, right? Chairs are going to fall apart, right, and so on, right? So it's you know, it's clear that interactions play an essential role, right? But yes, I've assumed that I know what systems are, to some extent.
Just one last question.
It's sort of a dumb question, but in the invariance was sort of crucial to this showing the wormhole, but it seems naive at attention with sort of it not being present in classical systems and, you know, are very quickly decoherent to look classical. So to what extent what are the conditions for the invariance to be, you know, operative symmetry in nature?
So I think you can extend invariance in various ways, and you know, I mean, the tricks that I used in making amplitude equal near the end. So the question is, you know, you really use it to explore geometry of the Hilbert space, right? And you know, if the system is mixed, then it probably has something it's entangled with somewhere there. And the question is, you know, is the state locally such that it can be transformed in ways which do not mess with whatever's there, right? Or can you somehow complement it? And the answer is generally yes, right? I mean, if you have a density matrix, you know, you don't really have to worry. I mean, you know that the density matrix has Schmidt states on the diagonal, right? So you can ascribe to them probability safely, right? Sure, that's it.